Muted.
Okay, let's go ahead and get started. Welcome. Let's get some feedback here. There. So I see quite a few people here. I see Edward, James, Ridge, Stephanie, and Tommy. And glad you're here. Whenever you have a question, just unmute your microphone and go ahead and ask it whenever you have it, and I will answer it at that time. Here's what I have planned to do now. If everyone can hear me, I'm going to have you, if you are on the web, I'm going to say, if you can hear me, respond in the chat. There. So, oh, good. Thank you, thank you, thank you. All right, very good. So I'm going to go ahead and get started. Wasn't sure that it was going. It doesn't always, but it is this time. So here's what I want to do for the next hour. You can stay the whole time if you wish, or you may choose to early if you have to. So what I'm going to do is go over some information from Chapter 1, 2, and 3. Specifically the information, I want to focus on what will be on your things that you'll be working on and that you'll be asked to take in the coming week. I'm also doing a couple problems from Chapter 2 homework and also bringing that up to Chapter 3 homework and then answering any questions that you have. So to begin with, oh, and one other thing, I'm recording this right now, so just to let you know, if you do ask questions, what you ask will be on the recording. Then because I'm doing it here on RSU, it has to be rendered, the video, via the Center for Teaching and Learning. If I do it at home, I render it myself. But here they have to do it, they've already gone home. So I won't be able to post it tonight after all. I'll have to wait to post it in our online course tomorrow. So that is, that's what we're going to be doing in the next hour. Let's start with Chapter 1, and we had basically an introduction to what this course is all about. Quantitative methods is this body of knowledge that uses numerical quantitative approaches to decision making, and that is sometimes called management science. It's sometimes called operations research. It's sometimes called decision science. We use a lot of linear programming in this class. Almost half of the class, in fact, is linear programming. However, it's not really computer programming at all. We can use computer programming to solve a number of the problems, but this has its early roots in World War II, and it was used in the military, developed in the military as a logic to try to maximize profit, minimize costs based on a number of constraints that were required of the military. So although we can use a computer program to do it, linear programming is not computer programming. It's logic, as you've seen with Chapter 2. Why do we experiment with models? Actually, you answered this nicely in your Chapter 1 homework. It takes less time if you have models to play with than if you have to wait for a real live situation to play itself out. It's less expensive because you don't have to pay for a real life scenario, and it's not risky, hence model. So that's why we use models. Now when we talk about linear programming, as you know, there's some basic concepts that Chapter 2, 3, and we're not doing Chapters 4 or 5, we'll be doing Chapter 6 next. They all start with this objective function, and that's that mathematical expression or a line or formula that describes what it is that we're trying to do. We're trying to maximize profit or minimize cost. We're trying to make product A and product B, or product X and product Y, and we know how much profit we make on A and how much profit we make on B, and those are what go into our objective function. The useful thing about quantitative methods is that most business situations have constraints to which product profitability is constrained by. And those constraints are expressed in mathematical functions or lines as well. So here's an example of a mathematical model to use linear programming, where we are maximizing some objective function, and it's subject to several constraints. And so that, in sort of overview, brings us up to Chapter 1. And I think you found that you could read Chapter 1 pretty well. Starting with Chapter 2, when it gets quantitative, it's not quite as easy to read. So the best way to understand it, starting with Chapter 2, is just simply do some problems. So what I wanted to do was start with problem 23 to make sure everyone understood it. And in so doing, you can ask problems as we go through. As you recall, problem 23 from Chapter 2 was for Embassy Motorcycles, and they manufacture 2 different models of these lightweight motorbikes. And we were asked to formulate a linear programming model to maximize the profit. So the first thing to do is to conceptualize this quantitatively. So we're going to make it. It takes I guess we could use easy writer model as the entire variable name, but that takes a lot of space and time to write out. So it's just easier to just, let's call it E. It doesn't take as much space and it's quicker to type. And we'll call the lady sport model an L. So we know how much the profit that Embassy Motors makes on an easy rider motorcycle. They make $2,400 for these little things. They're just little for teenagers. And they make $1,800 for every lady sport that they sell. They're new entrepreneurs. They're not making a lot of money, but they're making enough. So for every easy rider that is sold, they'll make $2,400. For every lady sport, they'll make $1,800. And we know that there are 3 different constraints to which this objective function here is subject to. There's only 2,100 hours of engine time available because our family makes them in the garage. And we can make maximum 280 lady sport models because that's all the frames that we have available. And there's 1,000 hours of assembly testing time. That's all that's available there. So we know that every easy rider takes 6 hours to build an engine, and every lady sport takes 3 hours to build an engine. However many of those easy riders or lady sports make, we have no more than 2,100 hours available for all of that. And similarly for assembly, we know it takes 2 hours for every easy rider, 2.5 hours for every lady sport to assemble it and test it. And over the month time, we have no more than 1,000 hours. We could use less if we needed to, but we don't have more than that's all the family members we have to work on it. So how would we solve this problem graphically, like we've been asked? So you can see my handwriting here. First of all, you want to define what we're trying to produce, which we have, E for easy rider, L for lady sport. Then draw each constraint on the graph. And I saw you doing this, but I'm just going over this to give you a chance for specific questions. So we had 3 constraints. The first constraint was engine hour time. 6E plus 3L cannot exceed 2,100 hours. So to draw a line, what do? You just need 2 points to draw it. So the easiest thing to do is to draw 1 point on the y-axis and 1 on the x-axis. So when E is 0, that means E is on the e-axis. That's 0. So we have 3L equal to 2,100, or L equals 2,100 over 3 equals 700. So here's 1 point here, 0,700. Same thing, if we let L equal 0, now we have E equals 2,100 divided by this 6, or 350. Well, there's a point right there. We also know we already have the line for lady sports. It will always be 280 on the x-axis no matter what that E is. So going to the next screen. So here's the third constraint. 2E plus 2.5L cannot exceed 1,000 hours of testing and assembly. So let's let E equal 0. Then we have 2.5L equals 1,000, or L equals 1,000 over 2.5, which is 100. Similarly, if we let port be 0, then E equals 1,000 divided by this 2, or 500. And I saw when I was grading your papers that you got that well. So now you've drawn this. So we say we've got points for each of the 3 constraints. Let's draw each of the 3 lines. So here's constraint number 3. When E equals 0, we have E on this axis, the horizontal axis, and we have L on. Someone might want to mute that a bit. So let's draw that. When E equals 0, L equals 400. So I didn't draw that. When L equals 0, E equals 500. So this point is correct, and this should be coming up right here to this point right there. I drew this a little bit late last night, and it's not quite there. Just pretend that it's drawn there, like so. We still need to draw these 2 constraints. L is less than or equal to 280. So 280 is right about here. So no matter what E is, L will always be 280. So that's a straight line right across this way. And the other line to draw is this first constraint for engine time with 2 points, 0, 700 and 350, 0. So looking at that, we have 0, 700 and 350, 0. Now we have constraint number 1, constraint number 2, constraint number 3, which is actually a little bit off here. So what we do is we know that by the way, each one of these constraints is less than or equal to, so we need to identify. First, we draw the constraints. Secondly, we identify the feasible region, which is everything that all 3 of those constraints have in common. It has to be less than this constraint number 2, less than constraint number 1 and 3. So this area here is the only area that is less than all 3 of those. So we've drawn the constraints, we've identified the feasible region. Now we need to identify the extreme points. Extreme points are all the turning points that surround the feasible region. 1, 2, 3, 4, 5 of these. You can call them 1, 2, 3, 4, 5, or you can call them A, B, C, D, E. I call them A, and you can start up here and do A, B, C, D, E. I just did this way, A, B, C, D, E. So now our job, since we have identified where the points are, is to identify what the points are. What are the coordinates at each of those points? So I've drawn it again here. Identify the extreme points surrounding the feasible region with their coordinates. Why? Because once we do that, all we have to do is take each of those coordinates for each of these 5 extreme points, plug it into our objective function, and calculate the profit made at each one of those extreme points. Because we know that the optimal solution will always be one of the extreme points. So we test each one of these points in yellow is a feasible solution. This out here is not a feasible solution, nor is this, nor this. It has to be common with all the constraints in order to be feasible. And the optimal solution will always be one of the extreme points. In this case, there are 5. So we know what extreme point A is. It's 0, 0. Right here. We know what extreme point B is because that with L is less than or equal to 280. So that means E is 0. This point is E0, and L is 280. So we've got that point down. C, well, we know that this is 280 on the L axis, but we don't know exactly what the E axis is. Looks like it's between, like 150, 200, it's hard to say. So we'd want to calculate that. We don't know what D is, but we do know what E is because we had to, we used it to draw that line. It was 500 and 0. So we know the coordinates for A, B, and E. We need to calculate the coordinates for C and D. So, and once we have those, we can calculate the profit, and bang, we've got the answer. So let's do that. Let's first solve for extreme point C, which is right here. We already know L. L is 280. So let's just plug it into extreme point to that constraint number 3, and which is 2E plus 2.5L equal to 1,000 hours available for engine. and L is 280. We knew that's what, you know what this is, because anything on this constraint here is 280. So plug it in 280 and do this math and solve for E, and we get E equals 150. Okay, so that was pretty easy. This is 150, C is 150, and 280. Okay, so now we're ready to solve for extreme point D. Since we know this, because that's 150, and E, the only thing we don't know is D. Let's calculate that. Oh yeah, I wrote that in, 150 and 280. So the only thing left now to do is D. Find out what D's coordinates are, and then we can plug them into our objective function to determine the profit. So extreme point D is formed by two constraints, constraint 1 and constraint 3. If we go back up here, we can, here, constraint 1 and 3 form constraint extreme point D. So that's how we know which lines to add together to solve and find E and L. So extreme point, or constraint 1 and constraint 3, I added them together, and then you can solve for either E or L in terms of the other variable. I chose to solve for L, which was 563.6 minus 1.45E. Now I took this value of L, plugged it into either constraint 1 or 2. Actually, you can even plug it into this sum of both of the constraints. It doesn't matter. You'll get exactly the same answer. I picked constraint 3 because it looked a little like easier math. So the 2E plus 2.5, and then I found up here L is this long thing here. So I plugged that long thing into L, and I solved for, you can see I had an error here. I forgot to put 2.5, but I fixed it. And I solved for E. I make math errors too, which is why I like computers. Okay, I solved for E, and here it is. I think I got 250.9, but purpose of this, I rounded to 250. Then I took, you can take constraint 1 or 2 or the sum of them, doesn't matter because you'll get the same answer. Plug E into any one of those 3 line equations and solve for L, and I get 200. So now we know E is 250 and L is 200 at here, at this point right here. Those are the coordinates now for D. So now we have everything we need to finish up this problem. We have now found the coordinates for each one of these 5 extreme points. So we take the objective function of 240E plus 1800L. You can see for E and L, I plug E in first, 2400, then L in with 1800, and I multiply it out, and I find out what the profit is. So at extreme point A, where we're making no, we're making no easy sports and no lady riders, well, of course, our profit's 0. For extreme point B, we plug those in, our profit with 0 easy riders and 280 lady sports, our profit would be 864,000. I have 864K. With extreme point C, we plug those coordinates into our objective function, and we have a profit of $504,000. And then we plug that in for D and E, and we can, after we get all that done, we say, okay, which of these 5 extreme points produces the highest profit? The highest profit I see is $960,000, which is extreme point D. That is why it is the answer. And we can then conclude that extreme point D at, whoops, I should say 200. That should say 200. Go back to that. I will have to fix that. So extreme point D was 250 and 200. There. Provides the optimum solution because it gives us a profit of $960,000, almost $1 million. Do any of you have questions about that, seeing that? On your exam that you'll be doing, I'm not going to ask you to draw anything, because if you're taking it online, you can't draw online. So what I do have you do is I will give you an extreme point in the coordinates and a maximum an objective function to maximize and ask you to tell me, if you know the coordinates and the objective function, which one's the optimal solution. All you have to do is plug each one of these coordinates into the objective function, determine what the profit is, and pick the one with the highest profit, and that's the answer. And that's the important thing that I would expect these students to be taking with you, understanding the broader concept. Anyway, I think you'll be relieved to know that that's actually the only math I think I'm asked you to do on the exam. The rest is concept. And there'll be no drawing. Comments? Okay. If you do have comments, you can, and you wish to type them in, I will look at the type count to answer that way too. Okay, so that was problem 23. When you got to problem 45, this is the one where I noted in the course side and on syllabus that you could use the online simplex method tool if you wish. And it sets it up here. You're maximizing. Your objective function is here, 1a minus 2b, and it's subject to 2 constraints plus the non-negativity constraints of a and b. You could do this just like we've been doing the rest. First, determining the coordinates of these 2 constraints, drawing both constraints, identifying the extreme points on them, plugging those extreme points of coordinates into the objective function of here. Whichever coordinates produce the highest profit would be your answer. Or you could use a simplex tool. So that is what I have here for you to see. Let me make it larger. Zoom it up a little bit bigger. You can see my colleague's email. Okay, so here's what you do. Well, I'm going to start from the scratch. In case you've not used this yet, you can use this for Chapter 3 problems. So the first part of the Chapter 3 problems give you some expensive printouts from an expensive computer software printouts for you to interpret, dual values, etc. And then the problems that you're asked to do, use this online tool. And all you do is take, and this is on the class, it's on this site online in several places throughout the classes, as well as in the syllabus. And you can start from scratch here, just paste it into your browser to get to it. Or you could Google for it too, Google simplex method model for more than 2 variables, and here you have it. So what you do is you get this, that you see this there. I'm just trying to make sure I have this. Good. Okay, so you get this screen, and you're wondering, well, how this has to be precise. Yes, it does. So if you come here where it says example, right here, and click on example, poof, you get this exactly how the linear programming problem format must look like. It has to say maximize or minimize. Make sure you maximize or minimize whichever problem is telling you to. And you must put in P equals, I think for profit, equals. And then here is where your objective function is. It gives you an example of a kind of a crazy looking objective function. But that's where you put your objective function in. Then it has to say space subject to, spelled out. Then you must have your constraints all on separate lines. And as you can see, you have to use less than or equal and equal to separately, just like it shows here. And down on the bottom, down here, you'll see notes on formatting about variables, etc. If you have questions about this, let me know. By the way, I've had a number of students with questions about Chapter 3 ask for extension on Chapter 3 problems. You may turn in your Chapter 3 problems by next Tuesday. I'm giving you a 1-week extension if you desire it. If you turn them in by tonight, I will have them graded by this weekend. If you don't turn them in by tonight, then you won't have them before the exam, but you'll have the extra time to work on them. So if you are going to type, well, let's go back to this problem. I have already typed it in, so it wouldn't take so long. But let's say if you wanted to type it from scratch, you could add in plus 4y. You can have 20 different variables here. I'm not even sure what the limit is for the number of variables you can have on here, but you can type in as many as you want. So I have typed in the problem already for this chapter, problem 45 from chapter 2, and I put it into there. I've maximized profit equals, this is the objective function, subject to these constraints, and then you just click on the button solve. And let me just start from scratch so you can see it pull up. I'm going to erase everything. Okay. You type it in, or actually what I like to do is to type it into Word so I can look for any typos. The average person makes a typographical error every 60 digits, including me. So I type it in Word and see if I've got any, like I have a plus instead of a minus, or I've put C instead of B. I check it over, then I copy it and paste it right into this window. Then I click on this button here, solve, and poof, there it is. Here's the solution. Pay no attention to the tableaus. The tableaus is the matrix algebra that you had to do when you took college algebra and you wondered what you'd ever use it for. If you're a computer programmer, you'd be using it a lot. But we're not computer programmers, and I don't want to see it. All I want to see is your objective function that you typed in, your constraint, and your solution. The opposite solution is $3 profit. With this objective function and these constraints, the optimal solution, the most money that can possibly be made is $3, and you can make $3 by producing 3 Model A's and 0 Model B's. That's problem 45. And when you're ready to copy and paste this into your homework, I suggest you simply click on your print screen button on your keyboard. Like, you can't see me hit my print screen button, but I did. And then come to, you can pull up Paint, like so, and crop. And notice all I need is this piece, crop. It shows what the objective function is, and the constraints, and the optimal solution. And I need, when you submit this, I need to see all of this for a couple of reasons. Number one, because if you don't have the right solution, it's okay. But if you don't, I want to see what your objective function was and your constraints, so I can look it over and tell you where your error was. Chances are you've got one little typo someplace, and you spent 3 hours trying to figure this out. So also, if you copy and paste this in an email to me and say, help me, what did I do wrong? I'll look at it and tell you. Occasionally, so once out of every 4 semesters, there'll be one student who tries to be creatively dishonest, and we'll see in the back of the book, you probably notice that some of the problems have answers in it, and they won't be able to figure it out this part, so they'll just type in the right answer down here and hope I won't notice, and I'll say they don't have the right objective function. So please put all your work in. This is not about getting the right answer, it's about learning it. So that is that. And that's how you use this particular problem solver. So much easier than doing it by hand. So let's go back to the PowerPoint. There we go. Any questions so far? Okay. And again, I'll be posting this. It has to be rendered. This whole video we're making right now has to be rendered by Center for Teaching and Learning when they get back in tomorrow after 8. So I won't be able to post it to the site tomorrow. And by the way, I will be sending out an email to tell everyone they can have an extension on their Chapter 3 homework, and they have to have the exam done by next Tuesday as well. And you can ask me more questions. I want to give you the space you need to learn this material. Oh, here's an example where I copied it and pasted it in. And what is this? The solution is a maximum profit of $3 by making 3 A's and no B's. And that's what 3 A's and no B's means. It means the coordinates of that extreme point. Okay, so that brings us to that concept of slack and surplus that you did in problem 20 of chapter 2. Slack is the amount that the left-hand side of your constraint is smaller in that value on the right-hand side of the lesson sign. When you have a less than or equal sign, it's called slack. If I were making up the words, I'd probably call them the same thing, but then I'm not in the business, and so someone who knows more about this decides. We're going to call it slack. That's simply the amount of the unused resource. If, however, instead of a less than or equal sign in your constraint, you have a greater than or equal sign, it's called surplus. That's the only difference. It's called surplus because it's greater than. It's called slack if it's less than. Because if it's surplus, it's really the amount that's still exceeding some kind of minimum requirement. Like with the lady sports, we had a maximum requirement. We couldn't make more than 280. But what if we had a minimum requirement that we couldn't make less than 280? That would be, if there's any value to the right of the constraint, it'd be called a surplus. That's what slack and surplus are. And when you were asked in problem 20 of chapter 2 to use the standard form to calculate slack and surplus, standard form simply means you use these S's for slack and surplus. And by the way, you subtract S if you have a greater than or equal sign. You add S if you have a less than or equal sign. And this is in my podcast and in the textbook. But you have to look for it, and you have to listen to all the podcasts. But I do hear students tell me that the podcasts, when they listen to them, are very helpful in walking through the major concepts that they need to solve the assigned problem. I specifically pick up practice problems that are very similar to the assigned problem. So for problem 20, constraint 1 with A plus B minus the slack equals 4. So once you've solved know what the extreme point is, it was 3.4 for A, and it just happened to be B was 3.4. You plug the optimal solutions into A and into B and solve for S, your slack. When you do, you get 6.8 minus S equals 4, which cooks down to S equals 2.4. That meant 2.4 units of unused resource for constraint 1. And for constraint 2, you're asked to solve for that. Actually, there are 4 constraints. I just have 2 here. Constraint 2 is 3A plus 4B plus S equals 24. And it was less than or equal to. So this meant that you were trying to solve for the surplus for constraint 2. So since we knew what the optimal solution was, we already found it in chapter 20, from problem 20, 3.4 for A, and imagine that, 3.4 for B. You plug those into A and B, solve for S2, and you get, just so happens that's 24 minus 24 or 0. There's absolutely no surplus. That means, gosh, when there's no surplus, that tells you that's going to be a binding constraint. There's nothing left over. And that's what slack and surplus is all about, telling you how much is left over unused for the future, basically, and where your tension, your constraining points are. Questions about that? Okay. All right. Then that brings us to chapter 3, which is sensitivity analysis. And by the way, you noticed, I think we had 1 problem with 2 variables in chapter 3, and after that we had 3 and more variables. So in fact, from now on with chapter 3, and then with chapter 6, when we do that, will be multiple variables. And you definitely want to use that online simplex problem linear programming solver. So let's just start with chapter 3 and talk and mention some dual values. What is dual values? That's a major concept from chapter 3. It measures that the amount of increase per unit by increasing the resource on the right-hand side of the constraint by 1 unit. And when you, let's say the unit was in the Easy Rider and Lady Sports example, the first constraint had to do with engine building time. Let's say we increase that from 2,100 hours to 22,101 hours. How much does increasing the number of hours available by 1 hour or 1 unit change the amount of profit? That's what a dual value is. And why would we be interested in that? Because we want to know how much, if we the extra slack, or if we have slack or surplus left over, how much that's going to increase our bottom dollar, our bottom line. And that's what sensitivity analysis is all about. It's allowing us to play around with the amount of extra resources, increasing them or decreasing them, and also play around a little bit with the cost or profit of your E's and L's, your Lady Sports and your Easy Riders, and without actually having to lose money doing so. So that's what sensitivity analysis is about, and that's why we need to know that dual value, because it tells us how much we can play with those right-hand side values and increase our bottom dollar. And again, you can use, with sensitivity analysis, you can use this same old simplex model that we were just using before. And in fact, let me just pull that back up. Here it is. And let me make that a little bit bigger so you can see it better. There we go. Let's say, going back to problem 45, what if I wanted to play around, instead of saying we had 3, whatever, maybe that's hours of, we're making thingamabobs, and it takes 3 chassis. We have 3 chassis available to make these thingamabobs. What if we increase that by 4? You just click on, change it to 4 in constraint number 1, and click on solve. And look, hey, we can see the optimal solution. It didn't even change the optimal solution at all. This is the power of sensitivity analysis. It means we put more money and more chassis available, but we didn't get anything out of it. So we probably don't want to spend more money on that. What if, on the other hand, we increased, okay, that was 3. Let's try that with second constraint. What if we increase that one, make 1 more wheels available? So that changes the optimal solution. So we have no increase in profit if we put more resources into constraint 1, but if we put in more resources in constraint 2, we upped our profit. That's worthwhile. And instead of having to draw this, taking 45 minutes to draw it, we can just, with a couple of clicks of your keyboard, poof, you've got the answer right here. And you can even change the, come up here to your objective function, change the amount of your profit for A, and click on solve, and you can see how that changes the optimal solution too. So from now on, you've already had the glorious experience of drawing these out graphically, and now we're just going to use the tools, technological tools available to us to get quicker solutions, because as a business manager, your time is money. So you can use that. That's sensitivity analysis in a nutshell. No one's asking any questions yet. So let's, here we go. Let's, what do I have here? So on the exam, I do want you to know what a dual value is and what sensitivity analysis is. You are not asked to use this simplex solver, but I do give you, I give you a graph that's already pre-drawn, and I ask you, is looking at this graph and the constraints, tell me, does this graph show a feasible region, or is it unbounded, or I can't tell. Basically, I just want you to look at a graph and interpret it for me. And finally, I tried to imply this in the, I think, Chapter 2 form that I'm going to, in fact, I did say that I was going to ask you in your first exam to type up a linear programming model of yourself, your own. So you can go back and look at if you happen to answer that question in the Chapter 2 form, see what you put in. But here's what I want you to do. I want you to describe what you're trying to, in words, what you're trying to optimize. I want you to tell me what your objective function is and what your constraints are. I'm doing one right here just to show you. You have to think about it. let's say I have, well, back when, a long time ago in the 1970s, when I was in undergraduate school, I had a roommate of mine, and I decided we wanted to go on some kind of crazy diet and see if we could lose more weight. This is oversharing, but I'm just going to share it anyway. So what we did was see what would happen if we ate M&Ms all month and almost nothing else. So with this college diet, I have a new college diet here. We're going to eat nothing but Dove chocolate, popcorn, Earth Balanced peanut butter, and Kind granola bars. So the first thing I have to do is say, I don't want to write that out every time I put it into my formula, so I'm going to call C for the chocolate, P for the popcorn, PB for the peanut butter, and GB for the granola bars. So I've defined my variables, number one. Number two, I need to determine what my objective function is, so I'm going to minimize the cost. I'm trying to eat this crazy diet for as little money as possible because I was in college and I didn't have any money. It costs 65 cents for every gram, for one Dove chocolate. So I'm going to eat a lot more than one of those. It costs 75 cents for every cup of popcorn, 28 cents for every serving of peanut butter, and 36 cents for every granola bar. And it's subject to some certain constraints. I have to have at least 2 grams of protein. Well, there's 2 grams of protein in chocolate, 3 in, etc. So you can see I had to look this up online to see what the grams were in a serving of chocolate, popcorn, peanut butter, and granola bars, and many grams of fat were in each one of those 4 products, and then how much vitamin C were in each one of those 4 products. Only the granola bars had vitamin C. And so these are my constraints. Here's my objective function, and I already defined up ahead these what the variables be. And this is sort of a silly model. I would never eat this way now, but you can see this is what all it takes. And then I had done this on the side. I haven't shown it here. I've done the linear programming model. The optimal solution is to eat nothing but Kind granola bars because nothing else has vitamin C in it, and so I can't possibly get vitamin C unless I eat the granola bars. I think I have to eat 16 bushels of them. I might be exaggerating. So, okay, anyway, that is what I expect you to know for the exam. Those are the highlights, the most important and salient points of chapters 1, 2, and 3. And now I'd like to know what questions you have. You can type them in the chat if you prefer.
Hey, Dr. Milliken, this is James.
Yes.
I just have a quick question on dual value.
Yes.
So I was doing the chapter 3 homework, and it did mention, I think it was in the first one, maybe number 4, find the dual value for constraint number 1. And I got kind of stuck on that, and it sounds like we're gonna have to know something about dual value. Now, will we be writing a dual value, or are we just defining it?
You will not be calculating a dual value, but okay. You'll be defining it. But I do want you to know what it is. So starting with number 4, the dual value. Okay, so first of all, in problem 3, that's one of the problem 3 is in the practice problems I did in my podcast. So I strongly recommend that all students review the podcast. I know they're long and they're not fun. They're not fun to sit and spend 15 minutes per problem to see how I do them, but it tells you exactly how to do the next problem. So if you watch the chapter 3 podcast or the chapter 3 problem 3 podcast, you'll see me work problem 3. Now it tells you. Well, let me tell you more on that. So you'll see what the optimal solution is. The optimal solution is 48. So now you're assigned to do problem 4. Now, when you do problem 4, use this, come back up here. There. Use this linear solver, simplex solver, to put in the objective function here and your constraints here and click on solve, and it'll give you the optimal solution. I'll tell you now the optimal solution is going to end up being 50. So you're going to now, by just making that change that I think.
And that one, okay.
Yeah, exactly. Constraint 1 asks you to calculate the tool value. So that just means change the right-hand side value in constraint 1 up 1 unit. So I think it goes from 9 to 10. And then click solve. When you go poof, solve, it'll tell you the new solution. It's going to say 50. And so you say, okay. And by the way, I think it tells you in your textbook that the answer to number 3 was 48, so you don't have to calculate it by yourself. Even I did calculate it for you. And so the dual value is the difference between the optimal solution in problem 4 and problem 3, because you increase the constraint 1 right-hand side value by 1. So 50 minus 48 is 2. The dual value is 2.
Okay.
So
Thank
does that
you.
make sense? You're welcome.
Absolutely.
Okay. And then I think C asks you to determine the right-hand side range for constraint 1. What is it? I forgot what it asked us to do. Do you have some specific questions for me on the rest of those problems? Because this is a good time to ask them. And I can assure you that people listening have the same problem, same question.
Yeah, I think.
Applauding.
Are you asking me if I had any other questions on chapter 3?
Yes.
I really didn't. I just had questions on the dual value, and
okay.
I kept trying to look it up, and I saw that there was multiple variables on some of the examples that I was seeing. But now that you've told me, it's just adding 1 to the right-hand side and then solving the optimal solution.
Yeah, and it's a difference between the optimal solution when you change that right-hand side of the constraint by 1 and when you didn't change it by 1. And there'll be a different dual value for each constraint.
Okay. I think besides that, I'm really okay with everything else.
Wonderful. Wonderful.
This has been helpful, and I did watch your podcast on chapter 3, by the way. I just didn't catch it in there. Maybe I missed it, but those have been extremely helpful, just so you know.
Okay, good. Well, if you didn't catch it, then it might not be in there, and I might need to read. But I have to say that Hollywood would reject my recordings, and I probably wouldn't hurt for me to review them. But I'm working on it.
You're doing great. You're doing great.
Oh, why, thank you. Okay, well, I'm very glad to hear that you're feeling comfortable with that. How about anyone else having a question that you would like to take this opportunity to ask about? Oh, good. You're welcome, Ridge. Okay. Well, if you find that you have questions this week, email me them, or you can call. If I'm at a meeting, I won't get the phone call, so the email is usually the best way to get a hold of me. And I don't know that I've ever had a question I couldn't help a student with, so I strongly encourage you to do that. Anything else? Okay. Yes, Trevor's asked. Oh, okay, here's a few more questions. Let me see. Make sure I got all the questions. Oh, it is 2, right? Yes, Trevor. Yes, the dual value is 2, correct. And then I'm just seeing the chat. Okay, and then Trevor said, "Is this recorded to review for later?" Yes, it is. In fact, when we in a moment, I will hit the stop recording button, but I have to send the MPEG-4 file to the Center for Teaching and Learning, because it's on their network that it's being recorded, and allow them to render it and save it via YouTube. So they'll save it to a YouTube, and then I'll post it to our site. And they are gone until tomorrow morning. So when I do these at home, I render them myself. But since this is on CTL's network, it'll be tomorrow. And one more question was, oh, do we need a Scantron for the test? No, because the reason you don't need a Scantron is because if you're taking it at one of the testing centers, you're going to get a hard copy of the test. And as a reminder, it's open book, open note, calculator, although you'll only use calculator for calculating the optimal solution when you're given the coordinates of the extreme points. And but it's open anything except someone else's brain. You have to use your brain because you'll bring your brain to your workplace, and that's where this needs to be applied. And the testing centers know it. If you're taking this online, ProctorU knows it. I talked to them a couple times. And yes. Okay. Any other last questions?
Yeah, I have a question regarding ProctorU. That's what I'm going to use.
Okay.
Is there a time limit for that? I didn't think there was, but just wanted to be sure.
I put down a 2-hour time limit.
Okay.
Normally when I give this face-to-face, the class is an hour and 15 minutes, and most students are gone in less than an hour. But because this is on, well, for the testing center, I put down an hour and a half, just because it gives a little more flexibility because this is an online class. And then if you're brave enough to take this online, I put down 2 hours, just to give you a little sense of exhaling. So,
okay.
Just letting you know, it probably won't take you even. It probably will. I've had students finish it in 20 minutes, but I recommend you take a little bit longer than that. Probably the average amount of time is about 45 minutes, I guess. So you won't feel a time crunch. If there were, I'd put more time on it. Other process questions like that, like what to expect. Open book, open note. And just a reminder that when you do use this simplex model here and you cut and paste, oh, you can also go to your button here, your Microsoft button, and look for this snipping tool here instead of using the paint. And then you drag, poof, and it's copied automatically. You just file, copy, and then paste it into a Word document. Poof, there it is. In fact, let me pull one up. Pulling this up. There we go. And let's just call this problem 3, whatever it is. And then just click on paste, and poof, there it is. Now and don't forget, even though this is something students often forget in the beginning. They get so excited they got the right answer that they forget to answer the question. Maybe A says to solve the problem, but say, I need you to tell me what is the problem. What's the solution? There is the optimal solution is A equals 3 and B equals 0, or you could just write it 3, 0. And the profit is $6. It might ask you another question. Tell us what, it'll ask you to look at this and ask you, so make sure that you look at the question in your textbook and answer all the questions A, B, C, D. So don't just copy and paste this. Remember to answer the questions, which is the most important part, analyzing and interpreting the printout. Other questions? These are good questions. I'm hoping you're pleasantly surprised at the exam. I want it to be able to test your knowledge and that you've acquired over these last months almost, and that's the point of it. By the way, the next unit after this test will be Chapter 6, 9, and 10. Chapter 6 is more linear programming, but it's applied to new kinds of scenarios in the business world. And I would say 90% of my students tell me that they're so glad when linear programming is over. They found that to be the most difficult. So don't quit. Keep working on this, and you're getting through the hardest part up front. About 10% of students will tell me later on, I like linear programming better. Don't know which you'll be, but keep it up. Don't stop now. Okay, well, here's another question I see. It says, okay, here's a question that says, yes, my book is online through Yuzu. Do you need to print out the chapters when using ProctorU? No. I told them that I talked to ProctorU 2 times personally and told them that you can use anything except someone else's brain, and if someone else is sitting, it looks like someone's sitting next to you and feeding you answers, then of course no one in this class would do this. But I said, no, that's not allowed. But yes, you can use electronic books. And that means that you'll be toggling between screens if you wish. Now, if you don't want to toggle between screens, then you could print out the book. That's your choice if you wish to do that. Kind of expensive. Good question. Very good question. Other questions? This is a good time to ask. I will also say I'm aware that the forum is generally not students' favorite thing to do in the class, but it's also a good way to, by making yourself answer these questions in the forum, it helps you focus on what are the major concepts of that chapter. And then everything, once you get your mind wrapped around what the major concept, the purpose of that chapter is, it helps working out the problem. It helps you focus on what you need to do to work out the problem. Okay then. Well, I'm going to hang on here for a couple more minutes in case anyone wants to ask me any more questions. But otherwise, free to go, of course. This will be posted sometime tomorrow after the Center for Teaching and Learning renders it and sends me my YouTube. And other than, again, let me know if you have questions. You can turn in your Chapter 3 by next Tuesday if you wish, for no penalty. Just won't have it back in time to use to take your test. I wish you a good week, and so glad we had a lot of students come. And good wishes.